My name is Edgar Mendoza-Jimenez. I'm a PhD student in Carnegie Mellon University's Mechanical Engineering Department. And today I'm going to be giving a small talk on some of the work we're just finishing up and actually submitting for a publication in the process development for the selective laser melting of tungsten carbide and nickel matrix composites. This work was done under the supervision of Professor Rija Jayan and Professor Jack Buth in the Mechie department. I'm going to start off by motivating CERMETs and the fact that they are not just used for high temperature applications, but in particular, the CERMET that we will look into, which is tungsten carbide nickel. It's a CERMET that's used in corrosive environments because it's very good at being chemically inert. Now, at the high level, CERMETs can be seen by this simple flow map of manufacturing where you have a metal powder and the ceramic powder. Then you undergo some sort of material mixing. Then that mixed material, you undergo some part shaping, whether it's casting or powder pressing, what have you. Afterwards, the shaped part will then undergo some heat treatment, which will then cause the part itself to densify, removing internal porosity and thus strengthening our final part. Now, the issue with this high-level manufacturing process really is twofold. The first is a bottleneck at the part shaping. The established shaping techniques, like I just mentioned, the pressing and the casting, results in parts with limited geometry, and that's due to the inherently nature of the part shaping itself. And the other bottleneck is the heat and sintering treatments are expensive from an energy standpoint as well as a capital standpoint. They're wasteful, again, also from an energy standpoint, and they can cause changes to the part dimension, which means that you must design for that specific geometric change, which adds another layer of complexity to this process in itself. And with that, we being an additive, in particular metals additive manufacturing lab, realize we can possibly leverage our existing established metal additive manufacturing techniques to introduce a solution as to there must be a better way for CERMETs to be manufactured. And fortunately, we believe there is. And that's where we introduce our established additive manufacturing technique in the selective laser melting or laser powder bed fusion. This process is established for already making or fabricating parts from the same metals that are commonly used in these CERMETs. In our case, we're working with tungsten carbide nickel, and lo and behold, our lab has actually done work with nickel alloys and pure nickel materials. So perhaps we can actually use this existing established technology and leverage it to introduce a new sort of composite material in this experiment or in this machine in order to build up or 3D print CERMET parts. And so just for those of you who aren't familiar with what exactly this additive manufacturing process is, you can sort of think about it being as as a powder bed process where your powder bed, which is here, holds your part, which is solidified or melted onto a build platform. Now this build platform will lower, and this dispenser platform, which has our raw powder material, will raise, exposing a lump of new fresh powder. Then a recoater blade will actually come across and pick up that dispensed powder, drag it over onto the powder bed, creating a nice flat even layer. And any powder that doesn't essentially get deposited onto the powder bed will then just get pushed into the leftover platform you see here on the right. Afterwards, a heat source in the form of a terbium laser comes across, and using sort of micro-reflecting system, the laser gets directed onto the top surface of our powder bed and thus writing or selectively melting the powder, in the form of the cross section of that particular layer. The process repeats, the built platform lowers again, and it keeps going until you pretty much finish the final layer of your part. And of course, the user-controlled parameters or inputs can be laser power, the laser velocity, laser raster hatch spacing, which is simply just a space in between the rastering of the laser back and forth as it fills in the cross section of your part at that specific layer. And finally, the layer thickness, which is simply just how much your build platform lowers for every single layer. And in particular, we're going to be looking at two specific parameters, which are the former two, the laser power and the laser velocity, hence why they're in bold. Now, the selective laser melting, or SLM, of ceramides in itself can be quite a volatile and complicated process. If you look at this diagram here, you do have a composite powder lying on top of a substrate. Now, whether that's the build platform, the first couple layers, or essentially the pre-built part or the previous layers, what have you. So you have a laser that comes down, it melts your composite powder, and you get a liquid melt pool, which in itself has a lot of heat transfer effects going on, conduction from the melt pool to the composite powder to the substrate to the solidified track behind it, advection, or the flow of the liquid within the melt pool itself. You also have convection, heat transfer from the liquid melt pool into the argon gas, which is actually flowing across the top surface of the powder bed. So given the fact that this is a very complicated, very volatile process, it's pretty difficult to model this, especially when we are introducing a new novel material system like a composite powder. But with that being said, we would take an experimental approach, and we have a hypothesis where we believe there exists a processing region within selective laser melting that will only melt the metal, thus wetting the carbide that isn't melted, and therefore almost immediately solidifying the material as a cemented carbide. And because of that, our project goal is to analyze the effects of the process parameters, the laser power and the laser velocity, on the 3D printed parts of tungsten carbide nickel ceramides and identify the processing region that optimizes these properties. And to do that, we pretty much took on a series of experiments. The first being a simple single track experiment where we essentially evaluate the melting behavior of our composite powder as well as the melt pool or melt track size. Then after that, we leverage those findings to begin building up multi-layer prints. In this case, they're going to be 10 rows or 10 layers worth, about 1 centimeter squares. And there we're going to evaluate the porosity as well as any delamination effects, which are crucial whenever we're working with a new material system. And then from there, we'll leverage those findings to then build a three-dimensional part. In our case, we're just going to build some simple cylinders, and we're going to evaluate the microstructure that results from these process parameters, as well as any, just in our case, one, which is hardness, the functional property, which is a very important property, at least for tungsten carbide nickel. So I'm actually going to spoil the talk a bit. I like to start off by giving my upfront conclusions just to motivate the work even further and everyone has an idea of what's going on. The first conclusion is the fact that the melting behavior of tungsten carbide nickel, in our case, we used an 80-20 volume split, was successfully classified. So we actually did manage to fully melt this material system, and we, from there, were able to build up parts. Through a series of experiments that I just discussed, we created or printed high density samples with homogeneous microstructure and minimal byproducts, which is really great if you're looking to essentially try to build up parts for specific applications. And finally, we tested the hardness and we found it to be comparable to conventionally made ceramides. And it was only limited by the vaporized nickel and lack of fusion melting behavior, which both defect mechanisms are actually present for metal 3D printing in the same process. So that's very indicative that we can actually use this material system, and this material system behaves similar to a pure metal. So in our 3 experiments, we had the very similar experimental setups. We used an EOS M290 machine, which is an industrial metal 3D printer for the selective laser melting process. Within the chamber itself, it was actually an argon environment, but that doesn't mean that there weren't minor traces of oxygen in there. The machine uses an ytterbium fiber laser, which is about near infrared, around 1 micron in wavelength, and it had about 100 micron diameter spot size. And we just used a very standard 200 degrees Celsius preheat on the substrate. Now the materials themselves, all 3 builds were done with a stainless steel build plate. The tungsten carbide nickel powder was a novel, very unique composite powder, which, as I said previously, has an 80-20 volume percentage, 80% tungsten carbide, 20% nickel. And the average particle size was 30 microns, which is indicative of good flowability because we need to have a large enough powder particle in order for the powder to flow well and deposit nice flat even layers. But if you actually look very closely at this powder, the powder itself is almost like a pseudo particle composed of tungsten carbide nanoparticles below 1 micron in diameter. And these nanoparticles are embedded within an agglomerated ball of nickel. So if you look at these SEMs down here, you see how spherical these powder particles really are. And as we zoom in, the nickel phase, which is in dark, is really just an agglomerated ball, and then within it you have embedded tungsten carbide or light gray particles in there, which is very unique because this is new material or new powder system that we actually haven't seen before. So we were very excited to try this out. Now, with regards to the single track print experiments, as I mentioned before, our independent variables were laser power, laser velocity, and we just wanted to evaluate the melting behavior as well as the melt pool size of our powder. Experimental setup, we used 36 different power velocity combinations. We only did one layer of powder, 50 micron in thickness, and we did a total of 5 tracks for each combination for a total of 5 times 36 different laser tracks. Now, the way we got these power velocity combinations, which you see here, where the y-axis is the laser power and the x-axis is the laser speed or velocity, was by referencing actually a previous experiment done on the single track or single beads of a nickel alloy. So we were essentially replicating an experiment done on a pure nickel alloy as compared to what we're doing now, which is a nickel alloy with 80% tungsten carbide in it. And it was quite exciting to see that we got very close to similar results. Now, with regards to the actual results of these single beads, you see here we labeled all the green stars had full melting. In other words, our tracks were consistent in width and fully continuous. We had partially melting where our tracks were perhaps they had a very high deviation in width, or they were perhaps even discontinuous. And in blue hexagons, we essentially found no melting or no traces of a track whatsoever. And we used a logistic regression analyses to essentially interpolate and extrapolate these results. So that way we have a decent idea of these what we would call fully melted regions in green, partially melted regions in yellow, and light blue unmelted regions, excuse me, in light blue. So we found a zone where we can essentially use the laser power and laser velocity and be guaranteed full melting. And we worked with that and leveraged it to start to build up pads. And from there, we wanted to evaluate the porosity as well as figure or see if observe any delamination effects between the pad itself and the substrate. We use 18 power velocity combinations. As you see on the left here, most of these combinations are in the acceptable or full melting region of the single beads. But a couple of them we decided to do in the partial melting just for the sake of experimentation and see how porous parts we would get there. And the hatch spacing or the spacing between the rastering of the laser was a normalized hatch spacing where we multiplied the respective single bead width of each parameter set by 0.7. And of course, we stayed true to our layer thickness of 50 microns. And for this experiment, we actually did 2 pads for every power velocity combination, as you see here on the right, for a total of 36 pads. And just to quickly go over some of our results, I won't show pictures of every single pad for the sake of time, but here you see 5 different pads throughout the process region. And for this most part, porosity was pretty decent actually, below 3% in all of these. I mean, there's 3.2% here, but we get really high dense samples. Now, porosity here was measured using an image analysis technique, so it's almost like a 2D projected porosity. But one thing we did notice about all of our pads were the lack of delamination, which is really good in the sense that we don't see early heat buildup, which is what essentially induces the thermal warping that delaminates the pads. And so because of that, we took all 18 process parameters and replicated them to start building up three-dimensional objects, in our case, cylinders, as I mentioned before. And here our independent variables were laser power, laser velocity, excuse me, and hatch spacing. And we wanted to evaluate the resulting microstructure as well as in the functional property, which was hardness. And so we actually managed to build cylinders with a diameter of and height of 15 millimeters. Like I said, the same power velocity combinations were used, but this time we unfortunately had to increase our layer thickness to 70 microns. The reason for that being with the 50 micron layer thickness, as we started getting to higher heights or more layers, we started getting thermal buildup, which was causing thermal warping in the part itself. And that's simply due to the fact that the heat can't be dissipated fast enough and there's too much heat being concentrated within the part itself. So by inducing this thermal warping, our recoater blade would come across, and if the part was warped high enough, could come in contact and impact and thus shear off our cylinders. So in order, we did some problem solving and realized we can increase the layer thickness just a little and still build up parts, but make sure we don't come uh, in face to face with this obstacle again. And here you see our results. So very similar to the previous slides. I'm only showing 5 cross sections for the sake of time, and you can see these 5, excuse me, 6 are spread out all throughout the place, and you can see various degrees of uh, porosity, really. Granted, these are superimposed over the single bead regions, which were 50 microns in layer thickness. So it's almost like you have to actually take this threshold line and increase the slope. So therefore, D might actually end up being in partially melted regions for a 70 micron layer thickness. Hence why we see a lot more porosity in D here, very little porosity in C. In fact, those large pores are actually remains of a diamond polish, really. So that there weren't there before. But B has very low porosity as well. A has some porosity as well, not as much as D, E, and F, which are clear lack of fusion, but still some left over. We also did a chemical analysis using XRD on all our parts, but I'm only showing you these 6. You can compare that to the standard powder, which is the raw material before laser processing. So a couple things to note. These gray vertical bands all show tungsten carbide peaks, which are present in all of our samples, which is great. The purple bands, which is this band here, and this band here, are our nickel peaks, which are present in all our samples. Great again. Uh, 2 things to note. There is a nickel oxide peak slowly getting bigger as you further increase the laser power, but it's not present in our powder, which is probably most likely due to the melting of our nickel and then having some of it react with the very small traces of oxygen in our chamber. So it's showing us that the laser processing is inducing a little bit of an oxide formation. Not too much to worry about. These peaks, at least the magnitudes of them, are still present even in a lot of sintering techniques as well. If we look at another peak that's not actually in the powder either, is a tungsten 2 carbide peak, and it's present in all our samples. And I was very confused as to why we were getting that. Turns out at very high heating rates and solidification rates, it's possible that you can induce this unstable phase and keep it there and keep it due to the very high solidification rates. And this is only present in sintering techniques or liquid sintering techniques that demand very high cooling rates or high heating rates as well. And just to show the hardness results, so as you can see here very clearly, as our porosity increases, the hardness also decreases. That's expected, right? Porosity stress concentrators, which further reduce the ability for or excuse me, further increase the indenter's ability to further indent into the part. And if we're to zoom in here, we start to see that at very low porosities, we are approaching the maximum value, which is predicted by the manufacturer of our powder, which is about 67.5 Rockwell C. And if we fit this trend here with an exponential fit, we see a very decent fit here. All our parts are well within the determined or predicted exponential fit. So if we can further optimize our selective laser melting process of this material system, we can further decrease the porosity and get closer and closer to that maximum theoretical value. Now, if we were to just take our hardness measurements and just project it on a different space, in this case, a laser power in the y-axis and a laser velocity in the x, and I'm also showing the standard deviation in our measurements through this color bar, we start to see that as you further increase the laser energy density, you start to increase your hardness, which makes sense because by increasing the laser energy density, we are essentially inducing more heating, which thus guarantees that we are melting and resolidifying all the nickel that's present in the material system. Now, as you see here, as I just mentioned, as you increase the laser power, you increase your hardness, but there is a slight noticeable drop off here, and I was very curious as to why that was. Why are we getting lower hardness values at a higher power compared to, which goes against the previous trend that I mentioned? Well, actually, if we look at the SEM microstructure, so for all our samples, we had a very homogeneous distribution of tungsten carbide nickel. We didn't really get any pockets of agglomerated tungsten carbide, which is very good for us because you always want to have a homogeneously distributed particle in your metal matrix composite. But what was very interesting is looking at these top two specimens, uh, we see that the nickel phase actually has a lot of pores. Now they're micropores, or excuse me, they're smaller than 1 micron, so they're very, very small pores, but they're pores nonetheless. And we realize that they're in the nickel phase. So we hypothesize that at these higher powers, we're actually causing our nickel matrix or nickel binder to vaporize, and that gaseous metal essentially induces a vapor pocket within our material. And because of the high resolidification rates, we are essentially resolidifying with vapor pockets inside. And that's what then causes the decrease in the mechanical integrity or hardness of our samples. So, in conclusion, uh, we show that the melting behavior of tungsten carbide nickel, an 80-20 long split composite, was successfully classified. Through a thorough series of experiments, we managed to print high density samples with a homogeneous microstructure and minimal byproducts. And finally, the mechanical properties, i.e. the hardness, were comparable to conventionally made cermets, and we realized that the mechanical integrity of the cermet is limited by the vaporized nickel at very high energy densities, as well as the lack of fusion porosity at much lower energy densities. And I always like to end my talks with a graphical representation of essentially what we did. So just to summarize, we took a novel composite powder that I have never seen used before. We classified its melting behavior using a simple single beads experiment that only takes about 30 seconds. We then leveraged those results to print 10-layer pads and realized that we were working within a very successful processing region. And through some minor tweaks in the layer thickness, we managed to build up tungsten carbide nickel cylindrical specimens that are comparable to what can be essentially done via conventional means. And this manuscript, we actually just finished writing it up last month, and we got it submitted a couple weeks ago. So we're looking forward to having it published in the Journal of Additive Manufacturing. And with that, I would like to thank my funding sources, both of my labs, as well as John Crane for providing a lot of the guidance and funding for this project. And I look forward to your questions. Thank you very much for listening.